Hi everyone, welcome to this online video where we'll be talking about Chapter 16, Chemical Energetics, but specifically we'll be focusing on the concept of energy profile diagram as well as the concept on fuel cell. Now before we talk more about the energy profile diagram, there's this concept of an activation energy that you need to first understand. Now activation energy is represented by the symbol of capital E with a small letter A and refers to the minimum energy that the reactant particles must possess in order for a chemical reaction to occur. Now, what does that mean? Right, let's take a look at the video first to have a better understanding of what activation energy actually means.
First assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's needed for a reaction to occur. The particles also need to have enough energy, enough speed, to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy. Some reactions require very little, and some need a lot more to get started.
In the flask are two large matches. It's being set on the hot plate, and the hot plate is turned on high. Matches have the red phosphorus at the ends, and when you strike a match, the red phosphorus, the friction, increases and the heat is produced, and that's enough energy to make the red phosphorus react with the oxygen in the air. Well, in this case, there is no friction. The heat being provided by the hot plate is enough energy to make the red phosphorus react. Here's a petri dish with some match heads that have been cut off, and again there's enough heat energy provided by the hot plate, the activation energy needed to make the red phosphorus react. Notice that the large match heads need more activation energy to start reacting than the smaller ones. Here it is again in slow motion, 4 times slower playback rate, and again you can see when the red phosphorus has enough energy, it'll start reacting. That's activation energy.
Alright, as you saw from the video, activation energy really refers to this certain amount of energy that must first be present in order for any reactant particles to collide and to result in a reaction. Now, whenever particles have energy greater or equal to the activation energy, and when they smash against each other, or what we call collision, this actually generates, or rather it kickstarts a reaction that gives rise to new products. But on the other hand, when reactant particles do not have that much energy, right, when they have energy less than the activation energy when they collide together, what will happen is that after hitting against each other, they will not form the product. Instead, they will just bounce off and go back to the other spaces around them. So remember that activation energy is the minimum amount of energy that's required for a reaction to happen. Now, what is it going to do with the energy profile diagram? In the previous few pages, we learned about this thing called the energy level diagram. Right. So the energy level diagram and the energy profile diagram are actually two different concepts, but they are very much similar to each other, except that in the energy profile diagram, you will have to represent the activation energy of the reaction. So just a quick recap. For energy level diagram, we know that it's represented in terms of some horizontal lines to represent the reactants, for instance, with a vertical line and an arrow to represent the enthalpy change, followed by another horizontal line to represent where the product's energy level is at. And this is what we call the energy level diagram. It's a bit like taking a leaf up and down a story of flats. Now, when it comes to the energy profile diagram, right, what we have to account for is this concept of activation energy. So it will look slightly different. So in terms of energy profile diagram, for the exothermic and endothermic reactions is as shown over here on the screen. But let's talk a bit about the exothermic reaction first. Now, in the energy level diagram, we know that for exothermic, the concept is to release energy to the surrounding. What this will mean is that we know that the reactant where they are and the product where they are should have a difference whereby there is actually a drop from where the reactant is to where the products are. So, as you can see in the energy profile diagram over here, you are still seeing this drop in the sense that wherever you're starting with in terms of the reactant and wherever you're ending with for the product is actually different from one another. But what makes this energy profile diagram different is that now there is this slope that goes upwards before it plunges down, and this is represented by what we call the activation energy. So what this means for us, it means that at the start of the reaction, the reactants will actually have a certain energy level, but only when it has this minimum energy of activation energy coming in, then will the reaction happen. As a result, it causes the energy to go all the way down to where the product is. Now, this difference in energy from where the reactant is, as well as where the product is still our enthalpy change, which is our delta H. This is similar to our energy level diagram. So if you were to recall, just drawing it below over here, this is our energy level diagram. For an exothermic reaction, you will also have the vertical line of the energy. You have over here your reactants, but instead of showing the slope to show the activation energy, you actually just represent the enthalpy change with the horizontal line to represent the product. Right? So it's rather similar, except that now you have to represent the activation energy before the reaction happens. So that's for exothermic reaction. When it comes to endothermic reaction, it gets a bit more interesting. You know that your reactants are supposed to start with less, and your products are supposed to end with more, right? But this time around, the slope will actually move all the way up before it plunges down, not all the way to the bottom, and it stops here where that is the product's energy level, right? If you compare this to the energy level diagram of an endothermic reaction, you recall that for endothermic reaction, the reactants is of a lower energy level, and the product is of a higher energy level. So this particular line is representing the triangle H, which is enthalpy change, which is represented by the products, right? So this is the endothermic reaction. But when it comes to the energy profile diagram, you actually have to represent a vertical slope upwards before it goes back to where the product is supposed to be. And this sharp increase up is what we call the activation energy for the reaction. And then this difference in energy is what we call the enthalpy change of the reaction, right? So I hope this gives you some perspective about what the energy profile diagram is compared to what the energy level diagram is. So essentially, what we are learning here is that energy profile diagram actually shows us the activation energy that's required for the reaction to happen, represented by the hump that moves upwards. So take note that for exothermic, it's a hump upwards before it goes back to where the product is, and then for the endothermic, it's a hump upwards before it goes back, but not all the way down to where the product is, because you want to make sure that there is an endothermic enthalpy change. So think of it a bit as if you are pushing a big rock across a slope. For an exothermic reaction, it's kind of like pushing up this hump, which is the activation energy, before the rocks go all the way to the bottom, and this is represented by the difference, which we will term as the enthalpy change. Similarly, or rather on the contrary, for endothermic, right, it's as if you are pushing a big rock over a hump before it rolls to a higher ground, and whereby you have this energy difference, which is your enthalpy change. So take note that for the exothermic reaction, the activation energy is just this portion, whereas for endothermic, it's a much bigger in comparison to where the enthalpy change is, right? So you can see the difference in terms of the activation energy over there. So that will explain what the energy profile diagram is. So in times of the questions that you come across, you have to read carefully to see if you are asked to draw the energy level diagram or the energy profile diagram. Next, let's take a look at the concept of the fuel cell. Now, a fuel cell actually refers to a chemical cell in which the reactants are continuously supplied to produce electricity directly. Now, even though we are learning about the fuel cell in this current chapter, we just like to let you know that eventually we'll come back to this concept again. You'll see this in the chapter on electrolysis again, right? And I think after having learned about electrolysis in class, you will have a better understanding and be able to better appreciate what you're looking at over here. But at this point in time, this might seem a bit abstract, and why are we learning about this in this chapter is because this chapter is about energy, right? And we talk about fuel cell is actually a form of energy source that allows us to power maybe our vehicles, etc. So one very good example of a fuel cell is actually the hydrogen oxygen fuel cell. And when you see the name of it, you know that this particular fuel cell taps on two chemicals, hydrogen, H2, as well as oxygen, O2. And based on how the chemicals react, it actually allows us to generate electricity to power different kind of vehicles or devices. So in your notes, you realize that you will see this term called an anode. You'll see this term called a cathode. Now, it can be a bit confusing at this point in time in terms of what is an anode and what is a cathode. Maybe just to give a bit of context, we'll take a look at a short video to understand about this concept of a hydrogen-oxygen fuel cell, and thereafter we'll explain a bit more based on what you see in the notes.
In order to obtain energy for the vehicle, we need to rejoin the hydrogen with oxygen, and this is done most efficiently in what is called a fuel cell. In an ordinary electric cell, a metal, say zinc, ionizes at one electrode, the anode, giving off 2 electrons. The electrons are pushed around the circuit, carrying energy to, for example, a motor, and are absorbed by metal ions of a less reactive metal, say copper. The circuit is completed by the movement of metal ions through the solution. In a fuel cell, the reactants are gases instead of metals. Hydrogen gives its electrons. The electrons flow round, driving the motor, and arrive at the cathode, where they are recombined with hydrogen in the presence of the reactive gas oxygen, which provides the driving energy to form water again.
So, as you saw from the video, a hydrogen fuel cell is actually a setup that makes use of what we call an electrolyte, which is an electrical conductor, as well as electrodes, which are usually 2 rods on the left and right side of the diagram. And this actually allows for a chemical reaction to happen, and the process generates electricity. So, just to put it into context, for this hydrogen-oxygen fuel cell, actually it allows for a chemical reaction to convert the chemical energy or the chemical potential energy to generate electrical energy for a setup or device or space vehicles in this sense. So what are the 2 reactions that happens? Because it's a hydrogen-oxygen fuel cell, the 2 reactions that it makes use of is actually, first, the oxidation of hydrogen, as well as the reduction of oxygen. So to represent the reaction that's happening, we actually have what we call half equations. Now these 2 over here are what we call half equations. As I mentioned earlier, you'll learn more about this in the chapter on electrolysis, but basically what they represent is the reaction that's happening at the cathode, which is a type of reduction, as well as the reaction that's happening at the anode, which is a type of oxidation. Right? So in case you have already forgotten about your reduction as well as your oxidation concept, right? Just a bit of a recap over here in case you're a bit lost. Now for oxygen, you recall that it has the oxidation state of a 0 because it's a free element, right? Whereas in the hydroxide over here, this oxygen, the oxygen state will now be a -2, right? So there is a reduction process that's happening. And if you look at the anode, the hydrogen over here, because it's an element, the oxygen state of the hydrogen is a +1, it's a 0, sorry. And then as it reacts, you will form H2O, whereby the oxygen state here is actually a +1. So there is an oxidation. So based on the reaction that's happening on the cathode as well as the anode, it actually allows for electrons to move. Once electrons start to move, that's where you get the electricity, right? And to represent how these 2 equations come together to show the overall reaction, we actually will add up both half equations together, and that's how we get the overall reaction. So just to give a bit more info, how do you get the overall reaction? We will add both half equations together, and we see how they will balance out each other. So what will it look like is that we will have the oxygen as well as the water with the 4 electrons from this part of the cathode reaction together with the reaction from the anode. That's where we will also have our +2H2 plus 4OH minus aqueous, right? Together, what will they form? They will form, based on the reaction, you can see that you will form 4 OH minus, and you also will form 4H2O plus 4 electrons. So this will give you 4 OH minus plus 4H2O liquid plus 4 electrons. But we don't stop here. We actually will cancel out things that's being repeated on the left and right hand side. For instance, the 4 electrons here and the 4 electrons, they will actually cancel out one another. Okay. Next, if you take a look at the entire thing, you realize that in terms of H2O, right, there's a 2H2O over here, and there's a 4H2O on the right hand side, right? So they will actually also cancel out, whereby you're left with only 2 H2O. Next, you realize that there's a 4 OH minus here, and then there's a 4 OH minus here. Similarly, they will cancel out each other, and that's actually how we end up with our overall equation that you see over here in the notes itself, right? So don't need to worry too much about this concept of half equation or overall equation at this point, because eventually when you go to electrolysis, that chapter, I think all these things will come more naturally to you. Okay, but this is just to give you an idea of how do we end up from this new thing that we call half equation to this thing that we call overall reaction. So essentially what this means is that as a whole, in the hydrogen-oxygen fuel cell, oxygen is basically reacting with hydrogen and then they form water. So that's actually why we call it hydrogen-oxygen fuel cell. And if you think about it, this is actually a pretty clean way of getting energy, because we are using these chemicals and you are actually releasing water, and water is perhaps one of the most neutral, one of the most harmless chemicals out there, right? Instead of releasing harmful pollutants like what you learned, like carbon monoxide, etc., or even greenhouse gases like carbon dioxide, right? So in a way, hydrogen oxygen fuel cell is very much preferred because it is considered a much cleaner energy source. So what do we need to know about hydrogen fuel oxygen cell? What do we need to know about hydrogen oxygen fuel cell? We need to know about what makes them unique and what are some of the disadvantages that they might have, right? So first and foremost, just to highlight that this hydrogen oxygen fuel cell is different from a normal battery because the reactants are actually not contained within the battery, but they are continuously being supplied from an external reservoir. Okay. In terms of the advantages of the hydrogen oxygen fuel cell or fuel cell in general, right? One of the key advantage is that these are actually what we call renewable energy sources, right, as compared to a fossil fuel. And the second one, like what I mentioned earlier, these are actually pollution-free fuels because they don't generate carbon monoxide or even greenhouse gases, etc. And last but not least, is a very efficient form of energy source in the sense that hydrogen actually releases more than twice the amount of energy compared to many other fuels. So it's not only clean, in fact, it actually allows for more energy to come out. Therefore, it's a more efficient source of energy. But there's also some disadvantages, right? I think first and foremost, it's very difficult to find a cheap source of hydrogen. Because hydrogen, in order to obtain them, if you recall, you actually learn about this thing called cracking of hydrocarbons in your ammonia chapter. Or a new way is actually to use what we call electrolysis of water. Now, both of these are very energy intensive, right? If it's very energy intensive, it will mean that it's very expensive also, right? So these are really not the best way to obtain the source of hydrogen. Secondly, it's also very difficult to store the gas. And thirdly, we know that hydrogen is a very flammable gas because you learn about your hydrogen gas test, right? The lighted flame and the extinguishable pop sound, right? So it can catch fire very easily and it's very explosive. Now, maybe just to elaborate a bit more before I end the video, why is it rather difficult to find effective way to store the gas? The main reason is because if you recall in the mole concept, right, every 1 mole of gas will actually occupy 24 dm cube of volume at room temperature and pressure. Now what this means is that to store hydrogen gas, because just 1 mole you actually require 24 dm cube, which is about 24 liters of space, right? If you want to store like enough hydrogen to maybe power your vehicles, you actually need a very huge container in order to contain the amount of hydrogen gas, because just because of the fact that this is how the volume of gas is like. Every 1 mole it actually occupies 24 dm³. Right? So to store hydrogen gas, we will actually need either a very large container, which may not be meaningful, because imagine you're driving a vehicle, cannot be the container is so huge, right? Bigger than the car itself. Or we will actually require a very high pressure container. But as we have learned in the chapter on ammonia gas production by Haber process, right? If you want to have a very high pressure container or high pressure setup, that will always involve a lot of money because it requires a machine, etc., etc. Alright, and with that, we have come to the end of the chapter on chemical energetics. Right, feel free to check the teacher if you have any parts that you're not sure about.